Next speaker, and I give you the exit. I won't steal you the 5 minutes. So. Next speaker is Sandra Giovannioli, and she talks about adaptive design and for treatment comparison.
Yes, I thought that I might share my thoughts with you on adaptive designs. I've been thinking about this topic for some time. So there's not a specific issue that I want to explain in details, but it's more of an overview. And the reason for wanting to do this is that adaptive designs, adaptive experiments are now becoming more and more popular, and in fact there is ever-growing interest in adaptive design, possibly, I think almost certainly, because of their connections with clinical trials. It's a mature subject in that some books are available and also some review papers. And clearly, from the point of view of applications, people want to know which design to use. And to statisticians is a rather meaningless question, depending on a lot of other things. Oops, sorry, I'm not. Okay, so I will concentrate on 4 points of interest to me. This is not a comprehensive list, of course. There should be many, many more on this list. The first one we've heard about already is inference after adaptive experiments. I'm talking about designs for experiments for comparing treatments, which on the whole seems a simple thing to do. You know, you got 2 or more treatments, so you have some units with some intrinsic features. You decide for each unit which treatment to assign, and you observe the outcome. In sequential experiments, this scheme is iterated, so you go round and round. And this is different from the two-stage design, or rather, it's not it's related. Sometimes what happens in a two-stage design, you have a fixed design to start with, and the second stage may be adaptive, or the other way around. But I'm not talking about two-stage designs at the moment. I'm talking about adaptive experiments, adaptive designs, those for which the assignment rule of the next treatment at step n depends on the past. And by the past, I mean past allocations and or past responses and or past covariates, including the present one, because I start with the covariates. Different names have been devised for different types of designs. In previous talks, I think all the emphasis was on response adaptive, meaning designs that are where the design rule depends on the responses. Fair enough, but it could and it should also depend on past allocations, and of course there is the problem of covariates. Short introduction to notation. It's more or less what you have seen in the previous talks. It's not different. What I would like to stress is, okay, we have an indicator function which is 1 or 0 depending whether the ith unit receives treatment A or B. I'm talking about only 2 treatments, mainly because for notational purposes, if you have many treatments, you have to use vectors. With 2 treatments, you use 1 scalar. So the design I describe as a conditional probability of assigning A at each stage. The probability could be 1 or 0 if the design is not randomized, if the design is deterministic. But in any case, because of the dependence on the past, the number of subject allocated, and a lot of other design quantities are going to be random. And from this point of view, the design points behave like data, very much like data. In particular, I don't know if other people use this expression, but I like to talk about design statistics, functions of the data of the design. That's useful. I mean, those indicated there are all design statistics. Okay, so inference, we've heard about inference already. The observations are no longer independent in an adaptive design because there is a dependent structure that is due to the design itself. It's a reasonable assumption, sometimes, not always, we can make this assumption that the observations are conditionally independent. Namely, when I observe the outcome after assigning one treatment to this one unit, it doesn't depend on the other units and the other outcomes. But conditional independence is not independence because the unit that I choose depends on the other observations. I don't mean the unit. I mean the allocation of the treatment to the unit depends on the past observations. And it's a well-known fact that the maximum likelihood estimators are the same, whether or not the design is sequential, is adaptive or not. But also, as we've noticed before, the inference is not the same because of the distribution of the maximum likelihood estimates, and it depends on the design. One observation about a point that came up before, it's about the consistency of the maximum likelihood estimators, which is something that we like. But to prove the consistency, you have to know something about the design already. And you can't use the consistency of the estimators to prove the convergence of the design, which you would be tempted to do a lot of times. If your design is a function of the estimates, you may say, okay, the estimates are consistent, converge, so the design converges, where you can't do that. Because you have, first of all, you have to show consistency. The other question is whether the inference should be conditional on the design or unconditional. In a lot of cases, people argue conditionally on the design. Is this justified? Well, sometimes it is. In particular, if the design is adaptive, but it's only allocation adaptive, it only depends on the past allocations, then conditional inference seems to be all right. But if the design is response adaptive, then the design itself is informative about the unknown quantities, so it can't be ignored. This is an example of what happens when you argue conditionally or unconditionally on the Fisher information. So the top one is the usual Fisher information for the binary case that we know, where pi is the proportion of allocations to the first treatment. But pi, of course, is random, and if we take unconditional Fisher information, maybe we have to take the expectation of this with respect to the distribution of the design. So we have a different information matrix on which to base our inference. This is perhaps a more illustrative example. In order to calculate the unconditional information matrix, we need to know the distribution of the design. And for finite sample sizes, sometimes in general, this is difficult. Asymptotically, it may be possible to do this. So in particular, if we take a design that is as follows. We take the name on allocation proportion that satisfies nice properties, as we know, minimizes the variance of the estimated difference. Okay, this name on allocation proportion depends on the unknown parameters, on the unknown variances. So we define a design, as we've seen other designs just before this talk, to proceed sequentially estimating the unknown parameters. And if we do this, we do actually get convergence to the ideal allocation, to the name on allocation. However, when we look at the asymptotic distribution of the maximal likelihood estimates, it is normal, but with a different variance from what we expect. And the reason is, in other words, we have a variance which is not sigma 1, an asymptotic variance is not sigma 1 squared, but it's got another bit that depends on the variance of the other treatment. And this is due to the design. Okay, so I've taken the expected Fisher information, expected with respect to the design distribution, but this is not the only possibility. I'm saying that I argue asymptotically taking the expectation, but a lot of people do other things. So the reason why I wanted to mention this is that this is very much an open problem. There is not general agreement on what to do when we want to make inference after an adaptive design. These are examples of what some people do that is in contradiction with one another, in a way. I've talked about Fisher information, but the same thing applies to power, of course. Power is random. So what do? Do we take expected power? Or we argue, like Hu and Rosenberger, by taking the distribution of the power function and use a normal approximation? I don't know. In particular, this has consequences on optimality. What do we talk about when we talk about optimality in the usual sense, inferential optimality of an adaptive design? An adaptive design is a rule for assigning the treatments, and it's a sequence of conditional probabilities. So what do we mean when we say that this design rule is optimal? Inferential criteria when n is fixed are the functions of the variance covariance of the estimators, or Fisher information, like, as we know, the optimality, A optimality, the power of the quality test, and other similar criteria. So when we say that an allocation rule is, an optimal allocation rule is, okay, I'll start again. When we say that an adaptive allocation rule is optimal, what do we actually mean? Do we mean a rule whose probability distribution minimizes the expectation of the power and or the expected information. This is a possibility for unconditional inference. Conditional is more complicated to explain what optimality means if we argue conditionally, because the conditional facial information depends on the design, but the design is random, so it depends on which particular realization of the design we obtain. So we really, by optimal, we really mean a stochastic process that produces realizations such that the conditional facial information is always optimal. I find this extremely hard to formalize, to make formal. So I have only started, and I'm already in deep waters. I'll change the subject. Okay. The second point I was going to talk about is the multipurpose nature of adaptive designs. Now, I maintain that the adaptive design rules are inspired by the sum or all, in general all, the following demands: inferential efficiency, maximum utility, and randomization. Now, inferential efficiency and randomization, we know this from Fisher times. It's always been there in design theory. So this novelty that now we worry so much about utility or ethics in the case of clinical trials is, in a way, it's a novelty that's been brought about, I think, by the actual use of adaptive designs in clinical trials. So this insistence. Incidentally, it's now other scientists are also worried about this efficiencies versus gain or utility. They call it exploration versus exploitation. Engineers call it that. But they don't worry about randomization. So, not to talk about covariates, or rather, we do want to talk about covariates. So now we have 4 things to worry about. And we need a compromise. This slide is not born of a sadistic attempt to scare you or make you think that I'm going to define all the those adaptive designs. They're not all the adaptive designs, some adaptive designs, and explain the differences and compare them. This is not what I want to do in this talk. What I want to do is really to put some logic, some rationale. Now, we start with inference. So if we start with inference, what is the best adaptive design? It's the completely balanced design that Linda talked about, A, B, A, B, A, B. Because that's balance, because balance is the optimality. Otherwise, if we're worried about A optimality, then there is the Robbins-Simon-Starr design that also is deterministic. But we don't want inference. We want, if we don't want inference, we want just randomization, then we have the completely randomized design. If we want both, then we have all the designs, adaptive designs, that worry about, they keep both, and it's permuted blocks. Linda has mentioned permuted blocks, bias scoring by Efron. Then there's another adaptive bias scoring by Way, and there's the Atkinson's DA optimum, and also ABCD by Baldi, Antonioni, and myself. Now, all these designs are meant to find a compromise between inference and randomization, and not just the ones I mentioned. All the EARN design, some EARN designs have also got that aim in mind. But we're not happy with just inference and randomization. We want utility. Now, if we want just utility, play the winner is the best. Also, up and down, to a certain extent, is motivated by immediate utility. I don't want to talk about the up and down because the up and down design requires a structure in the treatments. I'm only going to do the case of 2 treatments, so that's much simpler. Now, utility plus randomization, we got the randomized play the winner. We got the one randomly reinforced urn, but I think you used another expression, randomized reinforcement urn. But it's I mean the same. I mean the same one. Drop the loser, generalized drop the loser. Some failure-driven design by Atkinson and Biswas. Link-based designs. These are all motivated by two purposes, randomization and gain. And then we also want inference. At this point, there's another set of designs that were introduced to take into account all three. The doubly adaptive weighted difference design, the skewed DA optimum design, and then there is a large category that here I just described as compound optimal and constrained optimal. This is one, well, rather two large families. I will argue that these designs are different. There's a whole series of designs, some of which already mentioned. I think Linda did a very good job for me. Sequential maximum likelihood, doubly adaptive, bias coin design, efficiently randomized array, and also a fairly new one, reinforced doubly adaptive. Now, I put an orange color over them. These designs are interesting because they're machines, formidable machines for converging, for going where you want. And where you want is usually to find a suitable compromise between inference, utility, and randomization. So the design can be applied, the same design can be applied in lots of different situations with different targets, different allocations, but it goes there. It takes you there. And then we've got to do it all over again with covariates. Now, as I said, it is not my intention to go over it, but I would like to explain what the strategies are for finding these designs, and more, if you want. The basic strategy is to compromise at each step. So you've got two allocation rules. One is, say, for instance, the other one is for utility, for ethics. You compromise, and you do it at each step by combining the design rules, the probabilities. So I call this compound probabilities. The other way is a long-term one. We've got measures for inference, measures of efficiency, measures for ethics. So we combine our criteria, we find a target allocation that is the best possible for the combined criterion, and then we find out how to get there. So two different viewpoints, completely different viewpoints. And up to now, I think, well, this is almost true. Approach one is the most widely practiced, most widely used. So the compound probability. So I'll give you an example of one. Elementary design, completely randomized design, and completely balanced. So if we mix them together, if we do a linear combination, a convex combination, what do we get? We get permuted blocks, or we get Efron, depending on the weights. So Efron is a weighted average of two designs, one for randomization and the other one for balance. So, okay, the next slide is a bit of a provocation. If Efron can do it, why can we not? So shall we do the same? The following designs don't exist, but we can make them up. We can do a biased coin play the winner, combining the randomization with the play the winner design. The play the winner is the design that assigns the treatment that has been successful, otherwise switches to the other treatment. It's completely deterministic, no randomization. Let's do a weighted average with the completely randomized design, and then of course we can put everything together and do a combination of our Efron BCDs and play the winner, and we get a design that accounts for everything. So you see, the point I'm leading to is that there are so many ways, and now I'm going to show a lot more, of creating new designs, new adaptive designs. There's no need, well, is there really a need for more and more and more? But if you want to, if you need a quick publication, that's a quick way to do it. Instead of weighted averages, we can do a product. The product has got some, it's appealing, it's an appealing interpretation in terms of odds. It's either, a product of the odds or the ratio, or odds ratio. So so far we've seen sums and products, very elementary. Now, this is a bit less elementary. Rather than just do linear combinations and products, why don't we do a transformation of the probability? And how do we transform the probability? By taking into account a discrepancy of the present state from the ideal allocation. So if the ideal allocation is balanced, we create a probability that takes into account how far is the present allocation from balance, and allocates in proportion, with more probability if you're farther away. Now, okay, so linear combinations, products with powers, if you like, and transformations. I maintain that all the existing designs come from these three main ideas. Well, if not all, maybe 90% at least. So these are the three main ideas behind construction of adaptive designs. Incidentally, there is a symmetry property that I personally insist on. For me, it's important. The design rule should not depend on the names of the treatments. So it doesn't matter which one is A. If aspirin is A or placebo is A, the design should develop in the same way. There cannot be non-symmetric in the two treatments. Okay, now long-term strategy. I told you that this is a different approach, a completely different approach. So we can do two things. One is to have two criteria, one that reflects inferential efficiency, the other one that measures utility. You define a compromise criteria, find the optimal treatment allocation with respect to this compromise criteria, and then apply a sequential, randomized rule that converges to this target, so that you've taken everything into account. Another approach is constrained optimization. We put a constraint, again, you start with two criteria, you constrain one of the two and optimize the other under a constraint. The two approaches are not really different. It can be shown that they're almost equivalent. So they have a lot in common. There are difficulties, though. Criteria must be standardized. It would be a mistake. It would be very dangerous to compare things that are not homogeneous. So it's a good idea usually to have your criteria between 0 and 1, so you know, and both going in the same direction, both to be maximized or minimized. Otherwise, you get into a mess. So this is my warning. Don't mix together, like Kiefer says, apple and manure. Okay, this is an example, but I won't go into this. Constrained optimal allocation, we got this fantastic target, RSIHR, which we've seen, that is derived from a constrained optimization approach. And the constraint is on the power or the variance of the estimated difference, but the two are equivalent, I think. So if we minimize the expected number of failures under a constraint, we get this proportion, this ideal proportion. And it looks very nice because apparently there is no dependence on the constraint. Apparently. This is a tricky method. You may not realize that if you constrain, well, I'm sure you do realize that if you constrain variance, which depends on n, you get, and you keep your constraint fixed. Your constraint does not depend on n. You may choose your constraint in the wrong way. And I can give you examples in which you get that the optimal design has got, say, 4 observations or 10 observations, which is clearly absurd. So you've got to remember that, well, I think it might be wise to remember that the constraint should always depend on n as well as the unknown parameters. Is that okay, Bill? Okay, this is Bill's paper, so I'm a bit worried about criticism since he's here. Now, method 1, the combined probability approach, doesn't need convergence, or rather shouldn't need convergence as much as method 2, but they both methods do worry about convergence to an ideal target. So in other words, how is my design doing in the long run? Both approaches, and luckily we got some theorems that help provide the convergence, and not just the convergence of the design, but also the convergence of the maximum likelihood estimates and asymptotic normality of the maximum likelihood estimate. So that's helpful for the inference. So we can show convergence of a lot of common designs. In particular, this bottom one, the sequential maximum likelihood, that's again something that's already been mentioned, is when you start with some initial observations, and we've had a lot of clarifications about these initial designs for initial estimates, and then after that point, the parameters are estimated by maximum likelihood using all the data. The unknown target, which depends on the parameter, is also estimated by maximum likelihood. And the treatments are randomized with the probability given by the estimated target. So this was the example I gave you before. The target was Neyman. Neyman depends on the parameters. We estimate the parameters, and we allocate with that probability. Okay? But the convergence is very slow. This is a bad design. It's not a good design. The convergence is too slow. This is a design that should converge to 0.62, and it does in the end, but you see how long it takes. So why is that? Why is that? It's because at step n, the probability of assigning each treatment, or treatment A, is the current estimate of the target regardless of whether the present assignments are too few or too many. So if A has been assigned a lot of times, we don't take that into account. We just give it a set probability, and therefore it takes a long time to correct initial mistakes. Can we do better? Yes. Well, there are more sophisticated designs, and here we need another theorem to prove the convergence. The one I showed you before that doesn't work in this case, so we need another one. But the interesting thing is this. The slow convergence is due to the fact that the design is asymptotically normal. I'm not talking about the maximum likelihood estimates. Those are asymptotically normal. It's not what I'm talking about. It's the design itself. The variability of the design is such that the design, the probability of assigning it is asymptotically normal. Now, asymptotically normal means that the rate of convergence is square root of n. So it's a slow rate. What do? We compare the asymptotic variances. So if the asymptotic variance is smaller, the convergence is faster. And the design is defined to be asymptotically best if the asymptotic variance reaches its lower bound, which is a Cramer-Rao lower bound. Now, in particular, we have one design that we know with this. Okay. The arrayed is the one that's asymptotically best. But remember that this only compares convergence of designs that go to the same target. Otherwise, we find strange results. If we try to compare designs that do different things, we don't get any meaningful comparison. This is only for designs converging to the same target. Well, not all designs are asymptotically normal. Some are not. And those that are not are faster. So in particular, the ABCD has a fast convergence because of this reason, with respect to other designs of the same type. A final remark. Right, so there are trade-offs between speed of convergence, other aspects. There is no systematic way that I know of comparing designs with respect to some measures. Some measures have been studied, measures of performance of the design, like predictability that measures lack of randomness, loss that measures lack of efficiency. These measures are not applied universally to all the designs that we know. They're usually applied in the adaptive design context where the adaptation is to the treatment. So it's one type of design, so not in the response adaptive case. So there is, for instance, take an important design, doubly adaptive biased Cohen design. It's very important, widely used, because it's faster than the sequential maximum likelihood. What's the randomness? What's this selection bias of this design? I don't think this has never been looked at. So when we study designs, we tend not to look at all the aspects, only some. Now, simulations. This is a difficult topic because, first of all, what do I mean by simulation in this context? I do not mean simulating, say, clinical trials, which is also another important issue. Nowadays, simulating clinical trials is recommended because in order to save on time and patient health. But that's not what I'm talking about. I'm talking about the simulations that are carried out in order to compare the designs when we don't know the properties of a design, or in general, we don't know the properties of the design, then we tend to simulate. And in the adaptive design context in particular, simulations are for studying convergence, to see if the design converges or not, and to study the performance of some indicator, either for asymptotically or in general for small samples. Now, the simulating an experiment involves simulating the behavior of the physical responses, and in order to do that, we have to choose the true, in inverted commas, values of the parameters. So we pretend to be God, and we pretend to know what the parameters are. Okay? So this is potentially very useful, but also possibly misleading, and it may be inconclusive, of course. Why possibly misleading? Well, let's take I'm talking about something that I'm sure is very well known, but I want to remind ourselves that it's very dangerous to simulate unless you know the theory already. If you know the theory, you don't need to simulate. But anyway, let's take the birth and death designs. Let's take some urn designs. Urn designs is when the allocation rule is ruled by an urn process. So we put the balls in, pull the balls out. That's the process that changes updates the next probability of allocation. Take randomized play the winner. Why do I take randomized play the winner? Because it's the most popular one. People like the randomized play the winner. Now, the behavior of the randomized play the winner depends on the true values of the probabilities of success. So the limiting distribution is normal, but the rate of convergence changes according to the true values of the parameters. And in some cases, the limiting distribution is not normal. And it depends on the initial position. And also, okay, well, this is bad enough. So if I were a young student trying to understand how the randomized play the winner works, I wouldn't, because my simulations would be presumably done for some special values of p and would not reflect the general behavior of the design. So this is one problem. Another problem is this. Oops. The bottom line. The randomly reinforced urn design, when the two treatments are equivalent, P1 is equal to P2, the design converges almost surely to a random limit. Now, I want to understand what is the meaning of a design, an experiment that converges to a random experiment. What is the information there? It's very counterintuitive to me. So when I talk about convergence, I want convergence to a well-defined allocation probability. But when I simulate, if I find, what do I get from my simulations? A random behavior is a random behavior. It's very difficult to understand anything. Okay, so I'll skip the covariates and I come to the end. Thanks to the organizer for inviting me to Cambridge again. It's been lovely.
We have 1 minute for discussion. Yeah. Okay.
Please speak up. I can't hear you very well.
I just said the same thing. So, okay. Turn your. So I think one of the problems with simulations is it's average behavior, and you mentioned the fact about average power. Average power is not at all useful because clinical trials you do would be underpowered then. So you really need to talk about the quantiles of the distribution of power.
I was going to mention that in the earlier talk this morning.
So I think the only solution to the problems that you've given is to know something about the exact distribution. Because both the asymptotics and the simulated values that we have are not very informative about some of these situations. I'm not going to answer your C problem, but I'll just say that everyone mentions this RSIHR, but I think it all goes back to Chris Jennison. Is he still there? Yeah. Chris Jennison invented everything. Often not referenced, but he did invent everything.
By the way, for this tendency which you say, distribution, now a lot of people understand this and they introduce in pharmaceutical industry what is called probability of technical success.
Oh, God. Okay.
And that's actually what people do optimization instead of minimizing or maximizing mean. You usually maximize or minimize some quantile. And usually say, then you call this probability of success. That's quite popular now.
Sorry, I can't hear what you said, so you'll have to repeat it to me. You can do this.
Okay, I repeat again.
Okay, that's good.
So what I'm saying, now there is a very popular word in, say, pharmaceutical industry at least.
Yeah.
They talk about probability of technical success. Why? Because people started to understand that this average power means very much nothing in comparison of, say, two designs. Because basically people interested when your power, say, with probability 95%, will be greater than 80%. That's only in this case, FDA will approve your results. That's why people started to do this optimization problem not with average. Because average say sequential design, while sequential design is good, on average is better than usual, say, non-sequential procedure. But it has a distribution of stopping when you have to stop. And if you stop, it's probability 20%, at sample size which is twice as large as, you see, standard design. Who cares? In 20%, it's very high risk. So that's why they introduce this probability of technical success, and it's quite popular right now. If you go to some conference, pharmaceutical industry, you find out a few, whatever, it's called posters or presentations of young junior people who really talk about quite a bit.
Progress.
It really depends on the definition, because sometimes this probability of technical success is defined as average power.
But you see, each time you can find out people are different. And some of them are, okay, some of them are more equal. So, but it's popular stuff.
I think that's, to me, it seems a very nice statement to stop this, in particular since I urgently need a coffee.